Hello. Hey, look at that. That's what I did at the end of the last recording. I've given you to understand that source charges create a phenomenon that we call an electric field. The purpose or the effect of this phenomenon is that it transmits the influence from the source charges to the test charges, if there are any, and the result of that is the transmittal of a force from the source charges to the test charge. And so we imagine the electric field is the mechanism that enables the electric force to happen, even though the two objects carrying the charge never come into physical contact with each other. You'll remember the boat on the lake and me splashing the water analogy. The new thing, it's not really new, but it's sort of, now I have a way of really emphasizing it. Let me say a crucial idea here is that this phenomenon of the electric field is a property entirely and only of the source charges. It has nothing at all to do with the test charges. The electric field of the source charges exists whether or not there are any test charges around to experience it, in exactly the same way, in this case I do mean exactly, not just analogously, but exactly the same way that the gravitational field of the Earth exists whether or not there happens to be any object at a particular location in space to experience a gravitational force. Right here in front of me, right there is gravity. There is a gravitational field right there. There's nothing at that location other than a few air molecules, a few trillion air molecules, to experience the gravitational force, but gravity is there nonetheless. And anytime I decided to put a so-called test mass at this location in space, and as soon as I let go of it, of course, the gravitational force appears. Okay? Exactly the same thing is true for the electric field. For the gravitational field, the source of the gravitational field is the Earth, and that field exists, as I just said, whether or not there happens to be any object at a particular point in space to experience that gravitational force. Similarly, the electric field of the source charges exists whether there are any test charges around or not. And as you can see, and as you hopefully remember, the electric force on a test charge, if there is one, is then once you have the electric field, the calculation of the electric force that a test charge experiences when it's in that electric field, the calculation of that force is trivial. And this, in fact, is simply Coulomb's law, with all the complexity of the mathematics hidden inside this expression, inside this capital letter E, which is actually all of this. So the reality is, as a mathematical matter, that all the hard, meaning interesting, stuff is in the calculation of the electric field. And then, if the day comes that we ever happen to want to calculate the electric force on a test charge that's in that field, we can do that in an entirely trivial way. Remember, Q, charge, is a scalar. So this calculation is simplicity itself. So from this point forward, therefore, we're going to focus our attention almost entirely on calculating the electric field of source charges, and very occasionally will we remember to think about the electric force that that field would apply on a test charge. Okay. So that said, what I want to do in this recording is a fairly simple example for you, but it's going to cover all of the crucial ideas of calculating an electric field. Okay? And then having done that, then we'll go to more complicated examples. But the purpose of all these examples, of course, is to get you comfortable with the meaning of this equation and comfortable with being able to manipulate the equation mathematically, how to handle it. So let's start with our first example. Wait, before we do that, though, I'm sorry, I should do this. Let me make it clear what these symbols are. Okay, so E is the total electric field. I'm just going to say field at the point in space P where we're interested, that we're asked about. Okay, so maybe I should say P first. The point of interest in space, somewhere we want to calculate the field. We'll label that point where we want to calculate the field with the letter P. E is the total field at that point. N is the number of source charges that are contributing to the field. The total electric field, and we'll see this in mathematical detail in examples to come, the total electric field is the superposition, that is to say the vector sum of the electric fields of each individual source charge one at a time. J is an index counting variable. And its values run from 1 equals 1, 2, 3, dot, 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 all the way to n. Okay. Then that means that Q sub j is the jth source charge. So Q1 is the first source charge, Q2 is the second source charge, Q17 is the 17th source charge, Q sub j is the jth source charge, and so on. And then R sub j, and this is a tricky one maybe. R sub j is the distance from Q sub j to P. You saw in the previous recording I had 7 source charges. Each one of them had its own distance from the test charge. We were calculating force back in that recording. And so there was 7 different distances because there were to the test charge, because there were 7 different source charges. Okay, so that's kind of a nice laundry list to remember. And of all of these, it's possible to argue that this one is the hardest to wrap your head around, and of course, inevitably, therefore, the most important of all of these things. Or they're all equally important, but this one is, well, maybe I'm thinking it's most important because it's the hardest one to really come to mental grips with. So keep an eye on R. That's funny. Right. So with that said, now let's do our first example. Okay. All right, so we have a singly ionized helium atom. Presumptively, you've had some chemistry somewhere which tells you what in the world a helium atom is, what singly ionized means, but just briefly, helium is the second element on the chart. It has helium is the second element on the chart. It has 2 protons, and therefore the electrically neutral helium has 2 electrons orbiting it. Singly ionized means that somehow or other, and we don't have to care how, one of the electrons has been stripped away, so leaving just 1 electron for the 2 protons in the nucleus. The helium also has, I think, 2 neutrons, but neutrons don't have any electric force, they don't have any electric charge, they don't have any electric field, we don't care about them. So we have then 2 positive charges in the nucleus, and then the single electron at a distance from it at, as you see, 26.5 times 10 to the negative 12 meters. And so therefore, and now the question is, calculate the electric field of the nucleus. The nucleus, yeah. All right, so calculate the electric field of the nucleus at the location of the electron. Okay. Step 1, draw a diagram. So what do we have? We have the nucleus. I'm going to go ahead and draw in the neutrons just because, but again, they won't have any effect on the problem. So we have a proton and a proton bunched in together with a couple of neutrons very close to each other, and far away from the orbit of the electron, and their separation distance is distance that I will call r. Nice, because what? The radius of this circular orbit. We're not done with our picture yet, though. We wanted to now draw in the electric field vector that we're trying to calculate. Now, you're not experts on drawing electric fields yet, but I have told you about what the field for a positive charge looks like, what the field of a negative charge looks like. And so we'll do that. But we need to think about a couple of things. First of all, the nucleus contains 2 charges, and therefore, in our expression for calculating the electric field, n equals 2. And so we would have q sub 1, q sub 2. We'd have r sub 1 and r sub 2. That said, the distance between the 2 protons in the nucleus is something like 100 times smaller than the distance that from the nucleus itself to the point in space where we want to calculate the field. Okay, and so the tiny correction that we would obtain by treating each of the protons one at a time is going to be so small that it's not worth the effort. So what we will do in this case, when the two protons are so close to each other compared to where we want to calculate the field, that we'll just ignore. Then we'll treat them as a single point charge whose total charge is 2 times 1.602 times 10 to the minus 19th coulombs. So that's that, first of all. So we will treat this as a single object of charge 2e. The second thing, and this is the trickier bit, and one of the reasons I did this example, is it's not a trick question, but it's a tricky question. I mentioned the electron in the statement of the problem, and I drew the electron in the drawing. However, the electron, as it turns out, is not going to come into it. The reason, or the way you know that, is because the problem asks you to calculate the electric field of the nucleus. It doesn't ask for the total electric field of all of the charges. It certainly doesn't ask for an electric force either on the nucleus or on the electron. So the electron got mentioned in the problem only to define the distance from the source charges, the protons, where at what distance we want to calculate the field. Okay. So the electron is a slight diversion and doesn't actually come into the calculation, other than it helps define this distance. Okay. And therefore, the electric field that we're after is, I don't even need to put the electron there, since the electron can be anywhere in this orbit. I'll put it down here just to get it out of my way. It's the same radial distance. Okay, and so then at this location in space, the field that we want to calculate, we'll calculate its magnitude in a moment, and as for its direction, I told you before that electric field vectors of positive charges point radially away from these source charges, and so the total field there is going to point that away. We haven't calculated its magnitude, I'm only drawing a picture. If I were to take both of these charges into account, I would have to have two distances, R1 and R2, but because of the reasons I explained before, I only have one distance, and so I'm simply going to call this distance I only have the one distance R in the R hat direction. Okay. So that's our diagram. And second thing to do would be impose a coordinate system. And I'm not going to do so explicitly. I'm going to hand wave my way around this because, as you see, we don't really need it. Calculate the electric field, I need to know the source charges. I need to know the distances that the source charges are from the point in space where we want to calculate the field. And of course, the other thing I need is where is that point where we want to calculate the field? Well, the point in space where we want to calculate the field is evidently there. We draw the field vectors there. For those of you who've had a little more math or like to think this way, what I've actually done is I have chosen a polar coordinate system, and my origin is at the nucleus. Theta equals 0 over here, of course. We're not going to use theta, but just so you know. My theta equals 0 is here, and of course, as always, my theta increases in positive values when you rotate counterclockwise. Again, we're not going to use theta here, and then so r is equal to 0 here, and then whatever distance, 26.5 times 10 to the minus 12 meters out there. Okay, that's the coordinate system. No big deal, don't worry about it. And finally, now we'll solve the problem. Okay, we want the electric field. The electric field at the point P is, because of what I said earlier, we only actually will have one term in our calculation for the electric field, n equals 1. Not because there aren't two protons, there are, but we're treating them as a single object. whose charge is 2 times 1.602 times 10 to the minus coulombs. So 2 times E, remember the symbol E is the symbol for the fundamental charge, the thing I just sort of mumbled off, over R squared in the R hat direction. And so this is, K is 8.99 times 10 to the 9th Newton meters squared over Coulomb squared times 2 times 1.602 times 10 to the minus 19th coulombs divided by 26.5 times 10 to the minus 12th meters. Please notice that I am including my units at every step in the calculation. I want you to do that as well. Quantity squared, and then that's going to be pointing in the outward radial direction. And don't forget to square this. That's a common mistake. Students miss squaring that. Please don't miss that. And I cranked through those numbers, and I got 4.1 times 10 to the 10 to the positive 12. And as for units, let's take a quick look at that. Let's see. Newtons times meters squared over Coulomb squared. Meters squared. Well, let's see. Up here we have, yeah. So here we have coulombs to the first power. This is coulombs to the first power now. So that divides out with one of those coulombs, not both of them, just one of them. We have meters squared in the numerator here. We have meters squared in the denominator. So those cancel out. And so we're left with newtons over coulombs. And so that's indeed the units of the electric field. And it points in the radial direction. Okay. So that's the calculation. I think I'll stop there. At the beginning of the next recording, I will talk a bit about the significance of these units, and then we'll do another example.